All right, welcome today to week 3 of our R statistics workshop. And today we'll be talking about ANOVA, multiple comparisons, post hoc analysis, and cancer studies. Where last week, we learned to compare two groups using t-test. Well, this week we'll more learn how to compare 3 or more groups using ANOVA, which is called analysis of variance, and dive deeper into these multiple corrections as we test multiple things at the same time. So today we'll learn how to perform one-way and two-way ANOVA. We'll understand how to correct for multiple testing, conduct post hoc analysis to identify specific group differences. We'll learn how to visualize these ANOVA, visualize our p-values on our ggplots, and also apply non-parametric alternatives when the ANOVA assumptions are violated. Here are our packages we're using today. Things we've kind of used in the past are statics for R, CAR for Levine's test, ggpub for adding p-values, things like that. But all reasonable things we've seen before, but go ahead and add those all in for this lesson. So first, why would we want to use ANOVA at all? We already have been using t-test, they're working great, right? Well, here's the problem. So when we did 2 groups at the same time, that was really good, really easy, it worked great. But now we have more groups. And it's not working really, going to work out real great if we just keep doing t-test, okay? If we just keep doing this, imagine there's already error, right? There's already a 0.05 error that we're accepting, right, for significance. Well, if you just keep doing t-test, this error just keeps getting it higher and higher and higher. If you look here on the type 1 error rates, as we do, pairwise comparisons and as the number of groups increase, you can just see the false positive rates getting higher and higher and higher. So it's just not something we can do, You can just see how I'm just kind of increasing in a linear value as the number of groups going up linear. It's just a linear increase in that false positive rate. So what can we do here? What is the solution of this? Well, if we use ANOVA, it tests all of the groups simultaneously. It maintains that 5% error rate that we go for over everything, So we have the null hypothesis that all the groups are equal, and alternative hypothesis at least one group is different, right? So if anything happens, if there's any differences at all, we'll get a significance result, right? So by checking for this global significance, ANOVA gives this initial validation of a change between different populations, and that's great because it allows us to have kind of a first pass over the data to see if you really want to go into it further. Sometimes you have a lot of data, a lot of different experiments, and you don't know which ones you need to really put the resources in to go further. So this really allows us to know there is a difference here. It's significant. We should go further into looking at this. So first, we're going to create our own cancer research data set here. We're going to simulate it, and it's going to have basically different groups, treatment groups. We're going to look at cell viability in response to treatment, and some other factors like p53 status, age, things like that. And here's just kind of a little slice of this here. We have our sample patient IDs. We're going to have control and actually the treatment itself, actually different drugs for that treatment. And then we'll have cancer types. We're going to have 2 different cancer types, lung and breast, and our cell viability. How well is the cells responding to the treatment? We expect it to go lower. Cells doing worse, they're dying off with the treatment. Do they have p53 status, or what is their age group? Things like that. And just to do a quick summary by treatment here, let's group by treatment on that data, and we can see we have a pretty good distribution among all our different 3 drugs and our combination of drugs here with our viability. And we'll also make a gene expression data set across 4 different stages. So we'll basically have several different genes here, and then we'll have different clinical covariates, things like age, tumor size, did it metastasize or not. And here's kind of a slice of that where we see, for each patient, we have what stage their cancer's in, what is the expression of these 3 different genes, what is their age, how is this affecting the tumor size, and do they go to metastasis? And our third study is going to be a dose response study. We're basically going to have 5 different dosages, and based on different cell lines and dosages, we'll see, look at the cell death. And you can see here, just at the very top, this is just the first dose. different cell lines, and different modes of death you'll see there. So that'll be our 3 different data sets that we intend to work with today. So first, let's start off with the one-way ANOVA, the simplest one, right? Well, we can use one-way ANOVA when comparing the means across 3 or more independent groups for one factor. So for instance here, we're going to be looking at, we're summarizing by treatment here once again, and we just care about we're comparing the means of these groups, drug A, B, C combination, against the cell viability. What's the viability in this? So that's our comparison here, right? So we can kind of visualize this. We're just doing a GG plot as we've done before, GG box plot with GG jitter, and going to go ahead and plot that. We've done this before, very similar to our last lesson just last week, where we have our different drugs, and we have our viability versus control, and then we use GM density here to get our cell density plot. We could have done a histogram and overlaid densities, but I think this is just a nice, clean way of looking at all of our distributions. So as we do before, the first thing we want to test is for our assumptions, right? Are they normal? Is there equal variance? Things like that. So first, we're going to check our normal. We're going to look at do our Shapiro dot test like usual, grab our p-values as we've done before, and we're seeing here that we pretty much have normal distributions across except one. It's good enough. And then we're going to use our Levine test, the CAR package, just like we had before in the past. And we get over 0.05, so that means there is equal variance. That's good. So things are looking good. We have a normal distribution. It is equal. We do have equal variance. So let's go ahead and do our one-way ANOVA. Well, there's 3 ways to do this. I'm going to show you. Probably the most standard is to use the AOV method here. The AOV, just do cell viability. That's the response, right, by the different treatment that we have stratified into our different drugs, right? Our drug study, and then you can get that and look at the summary, and you can just kind of plot that summary and get some of the values here. We see that we have, we see a strong F value and a very low P value, so we're seeing a significance here. So by AOV, it's showing us there is significance. There is some difference between these groups. An alternate way you could do this is with more of the base version. Use one-way dot test and same intro, and then just say var.equal equals true. This is saying the variance is equal true. Variance is equal. If the variance was false, for example, you would use false here, or you would use the Welch ANOVA test. These will both give us the Welch ANOVA test. Kind of like before, for equal variance, and but we're doing good. We don't need that, so we're just doing the normal one. And one more way you can do it is just the tidy version, of course, ANOVA test, ANOVA sub-score test, and do that. That'll give you your tidy version, and we can actually plot that tidy version here, and we're getting the same results here: 60, 48, 48, low p-value. So we're seeing significance. One advantage of using the tidy version is it already calculates your effect value for you. So you have your effect size, your general effect size. It's supposed to be a solid effect size here, over 0.6, and we see a significance. So we do see that there is something going on that's significant there. There's different ways you can calculate the effect size. You can do it just using kind of by hand here. I showed you here, where you're just kind of calculating the different distributions of the sum of squares. And you can also do that using the omega squared version, and that's kind of complicated, but just to show you the way you can play it out using the very base ANOVA result. But really the easy way of doing it is just calculate the eta squared and omega squared using the tidy version, right? So you have eta subscore squared or omega subscore squared. Those are the 2 functions you use. You just drop in the result, bam, you get your effect sizes right here right away, 6, 9, just like we're seeing before, the same thing, right? And this is a large effect. We talked about over 0.06 is a large effect. It's 0.6, so man, it's super big, super large effect, right? So we know there's a really large effect here. We know there is significance. Let's look at the diagnostic plots to make sure there's not something we're not seeing that's throwing off the actual result. So to do that, one easy way you can do it is the base version and just put in the ANOVA result and do which 1 through 5, 1, 2, 3, 5. You could do 4 as well too, but it just gives you some of the QC plots, and on the right we see our nice QQ plot where it's along the line, where that shows we're normal. And our other three are, residual, scale location, constant leverage. They're all measures of equal variance, and as long as the line is reasonably straight, constant leverage factors on outliers as well too. But as we see, things look pretty solid there. And if we want to, so we can feel like we can go ahead with our assumptions and feel good about that. Okay, so now that we know there is a difference, right? Between these treatments, there is a difference, but what is the actual difference? ANOVA tells us there's a difference, but not which groups differ. So we need to do a post hoc test to actually identify the specific differences. And really, a post hoc test, that's what we did for the t-test. A t-test is a post hoc test in its own way. So let's just show different ones we could do for that. Well, there's more options than just the pairwise t-test. So the first one is a well-known Tukey's. I always say Turkey, but Tukey's. And you just basically do Tukey HSD, and you just drop in your ANOVA result. It gives you your answer here. The higher this difference, the higher this value is in the negative difference, the stronger the effect is on viability, because the viability is going down. And then also you have your P adjusted value here. And what we'll quickly see is really everything is significant except, so every drug against control is significant, combination against control is significant, and combination against each drug is significant. But if you compare each drug specifically, they're not significant. So there's not enough difference in the drugs themselves. However, against control, they are showing a good response. So really all the drugs are working pretty well, but they work best if they're together, it looks like. So we can just kind of tidy that up, throw that Tukey result into our little tidy here, mutate it down, make a significance column, and we see here we have our results here. We saw our significances here. I think drug A, B, C versus control, combination control, the top four are the most powerful results here. But also, it shows you your combination is better than just the drug alone as well here. And just a caveat here, if you wanted to do a post hoc for unequal variances, let's say you went the Welch way and it was unequal, then instead of doing Tukey, you would use the Games Hal test, and that would give you your values for that. We'll use that later, but just to kind of give you a choice on that. And let's kind of plot our Tukeys. It's kind of a cool plot here. I basically did a GM error bar here to put these in. Added a line here for 0. That's basically it. Other than that, it's just adding the points. Just kind of like a similar graph we've done before. And we can see all the error values here. We're seeing this really low difference decrease in cell viability, especially if combination against the control. So the drug is killing off the cell. That's good. Again, drugs against themselves are the ones that are not significant. So all looks good. So what is an alternative? What can we do besides the Tukey? Well, if you just wanted to compare treatments to control only, Tukey compares to every single combination. But let's say now I just want to do the drugs to the control, which is usually the most obvious thing I want to do, right? So you use this MOLT comp library and use the Dunnett test. And Dunnett test, you see this MCP treatment by treatment Dunnett ANOVA result, right? And then just summarize it, and let's take the result here. And if you see here, it's very similar. It's just doing we're just comparing against control only. And we're seeing everything instead of, again, just like we saw before. Another thing we could do is just do a simple t-test. Let's just do pairwise t-tests between everything, right? So we use pairwise t-test here in the tidyverse package, and we just do cell viability by treatment, and we're going to use the Bonferroni, the strictest p.adjust value method. Where you have FDR, you have a few other ones. Bonferroni, I like, it's the strictest. And we have our result there. And we basically see, if we look in the plot, we're just looking for the significance of each of them. And basically, we're just seeing if we use the Bonferroni, we're getting the same amount of significant comparisons as Tukey, which is showing they're not all, they're showing the same amount of comparisons. And Dunnett's 4 because it's throwing out the extras and just going against control. So this is just showing they all three have about the same result with pretty low p-values here. So just So you can use the Tukey, you can use the pairwise, you can use the done it for just control. Those are all ways of really handling it as post hoc. And remember, if it was unequal variance, we would have used Welch earlier, and we would have used the Gamehouse test. So that kind of knocks out, I think, the one-way ANOVA. And then let's just talk about how we can actually plot this. So let's go back and we just want to plot all our results. It's just a simple GG box plot, ggplot, treatment versus solubility, fill by treatment, fill by the x-axis. And that gives us our fill and our legend, right? And we do the GM box plot, GM jitter, so we can actually see the points themselves, right? And we're using the Veridius colors, classic theme. And for what I wanted to show you here is really our p-value comparisons. How do we actually add these p-values and lines on the plot? And unfortunately, there aren't that many good ways to do it. Now, you could go into Illustrator and do this, of course, by hand. You can use several different methods, but I think the one I'm going to show you today works the best, and it comes out of the ggpub-r package. And so first, if you want to just get your ANOVA itself, you do stat compare means, method equals ANOVA, and label.y equals where on the list, where on the y column it goes. The reason it dropped in the middle here is because 171 doesn't exist. So I probably should have put a 40 or something to get it down there. But if you want to drop that on there, you do the stat compare means, method equals ANOVA. Now for the actual pairwise comparisons, if I want to use t-test, it's really easy. If it is non-parametric, I use Wilcox, that's fine too. So if I want to use the very basic like t-test Wilcox comparisons, and I don't want to jump into the farther ones like Tukey and Done It, then this works great. See, like for instance, I do t-test. Here we're doing the Benjamin-Hochberg p-just method, for example. And then, so I'm doing my t-test between all my different columns, and I am doing my correction, and then I am now making my lines. Making my lines, I do comparisons, and I make a list, and then I just make a list basically of each one I want to make. So if I didn't have these lines, they wouldn't be here, right? So control to A is, control to A. It's this line right here. If I just left this one line out, I would have the other ones and not that one, right? And then I'm saying label P by significance. I could have also labeled it by the actual value itself. And let's say you use Tukey, you're going to get pretty reasonable ones. So how can you get around this? Let's say we use Tukey and we have the same, they're all significant, right? Well, we could just do a t-dot test and then go in an Illustrator and then change the actual numbers. That would be a way to do it if you wanted to use Tukey or Done It. There also is a method in ggpub-r that instead of stat compare means, it's stat manual p-value, but it's kind of deprecated in the new some of the new R's versions, and it's a little bit difficult to use. But there is a manual method to try to plot these on here, but I think you can pretty much always get around it because t-dot-test and Wilcox.test are pretty much going to give a similar answer, and you can adjust the p-values later if you need to. But that's kind of a way here to get those p-values on the plot in a manual fashion. All right, so now we've rocked through the one-way ANOVA. Well, let's go to the two-way ANOVA. When do we use this? Well, now we want to check categorical factors. We have two categorical factors, right? And we want to know the main factor of one, the main factor of two, and the interaction between factors. And really, that's what I care about. The interaction between factors is the power of the two-way ANOVA. So let's give an example. How to treatment and cancer type. So these are both categorical variables, right? Treatment, A, B, and C, D, combination, cancer, breast and lung. How do both of these affect the cell viability? All right. Well, let's first get the data together and form a two-way summary. So let's stratify by treatment and cancer type. So that's easy, right? We just do group by treatment and cancer type. And then we get some, summary statistics for there, and we get a feel for the data. And then let's go ahead, I'll make an interaction plot. This is kind of cool, I think. Basically, you just put in the two-way summary, and X is the treatment, Y is the mean, and this time we're grouping by cancer type. So we have our two different lines here, and we color the cancer type by our different cancers there. And really we just make a GM line with points and error bars, and we're using set 1 for the color, and we're basically just making two line plots right on top of themselves, right? But this gives us kind of a feel for how well the drugs are doing by themselves, and how well, it's like lung, for example, starts with the most and ends with the most. So really the combination really is doing a good number on the lung as compared to breast, you think. So you're like, a quick look at this and you're like, well, it seems like the cancer type may affect the treatment, but does it? We don't know. That's why we're looking into this, right? So let's go a little bit farther. Let's check our assumptions. First, we'll do our Shapiro test here. Looking good, almost all normal. I think we're good there. Let's do our Levine test. And our one thing I wanted to show you is, let's do our Levine test. And you had an interaction term here. Treatment multiplied by, instead of the plus, you have that interaction term to be able to check that out. And so we feel good about that. Equal variance equals yes. So we're normal and equal variance, so we can go the normal way. We'll do our AOV, cell viability by treatment and cancer type. Remember, interaction term is a multiplication, right? And then we just summarize that, and we see here a very interesting result, I think. Treatment has an effect. There's a significance there. But cancer type doesn't. So if we apply the treatment, there seems to be an effect no matter what treatment we apply, right? There's something going on in there. Not no matter, but there's a significance in there with one of the treatments at least. Cancer type, it doesn't matter which cancer type we are. It's not helping the treatment. But interestingly, there's some kind of interaction with the treatment, the cancer type. So it's kind of a weird. If you look at cancer type by itself, there's not a difference. But if you add on the extra information of treatment and cancer type, there does seem to be a little bit of interaction. So the cancer type alone is not causing this, but there's something going on with the cancer type. Which one you choose that's affecting the treatment, and that's maybe what we see with the lung with a little bit of pronounced difference there. So it's not like overall, but there's some interaction affecting it, right? Let's do a quick ANOVA test in a tidy way, so we can get it all really easy and check our values. And we see here, it's just a summary of the results. Cancer type is not significant, but the other two are, and they have a pretty good effect size. But treatment has a much bigger effect size. So treatment by itself is what's doing it, and if we have a specific cancer type, there might be a slight difference, right? And once again, we'll do the effect sizes. This is the easy way. This is the hard way on top, easy way on the bottom. Let's do the easy way at a squared for the two-way model, and that's just giving us our EDA at a squared value. Our effect size is the same one we saw above, and like I said, we're getting a large treatment and a small from the interaction term, right? We also could have done a very simple effects analysis on this if we had a two-way analysis. We just wanted to see a treatment affect the cancer type and nothing else, right? What we could have done is just group by cancer type alone and just done an ANOVA test based on treatment alone, right? If we saw treatment was a bigger deal, we could go farther, right? So this is just a simple effect of just treatment alone. And if we just do that and look at that, we'll see treatment is. So as we go in each cancer type, we do see a treatment having an effect. But when we look at cancer type as a whole, it doesn't seem to be the treatment's not working better significantly in breast or lung itself. And if you want to kind of just visualize this, we have our ANOVA values here, which are just saying that there's a difference in the breast and a difference in the lung. And we can do our t-test and like we did it above to figure out the actual differences. We just want to know, is there a global difference in breast and lung? We are seeing that. But what we could show here on top, if we wanted to put, there's not a global difference between breast and lung. So if you look at breast and lung on a global level, you do not see significance among them in the treatment, right? So while you see this heat map here, if you look at the lung, it really seems to be working a lot better than the breast. That interaction is probably seen slightly in lung as opposed to the breast. So now we've done all of that. So things have been working pretty good with our assumptions. Well, what about if these assumptions are violated? What do we do now? What is our non-parametric alternative? Well, that would be the Kruskal-Wallis test. So let's see what we can do here. Let's make some new data that's kind of skewed and not so beautiful. And then we're basically just going to look at, it's going to be very simple. We're just going to see if there's a low or high response. So we have a bunch of groups, low, median, high, very high, and is there a difference between these? Is there actually a difference in response between these data sets, right? So first we're going to look at the normal, and we're seeing, it fails normal. We're not doing good on normal here. So we want to maybe look at a non-linear alternative, non-parametric alternative. Let's look at the Levine test for equal variance with our skewed data. And we're basically just, like, once again, we're just trying to see if there's some response, some kind of response in this group. And equal variance, no. Oh, no. Okay, so we're not doing good. They're both bad. They're both bad. Now, remember I told you equal variance actually means more than the normality in these things? So it's kind of hard to tell what to do. It's non-parametric, probably should use Kruskal-Wallis, but it's also equal variant, which is more powerful. So do we use Welch? I don't know. It's kind of hard to say. Probably go with the Kruskal-Wallis here, but you could go either way. You can see if you just kind of look at the data, how skewed it is. You see here and here the non-normality, and the problems with some of the variants of the distribution. So let's just do both and compare. So let's do the Welch ANOVA test for our Welch ANOVA, our one-way ANOVA, and then our Kruskal dot test. That's what we use for our ANOVA, our non-parametric ANOVA here. And when we run those two, we get our results, and we're doing a tidy version, which is a Kruskal _ test for using the tidyverse on the skewed data. And I'll pop that down here. And one thing, the Kruskal effect size, instead of the eta omega, you use Kruskal F size right here, and that gives you your F squared, right? And that's just going to equal what I would have got anyway from the tidy. So effect size 0.7, looking pretty good there. So let's just compare both of these. The statistics are pretty similar. They both have 5 p-values. They both have, they're both significant. I think here you could go, they both show a lot of significance. You could go one way or the other, I think. I probably would go with Kruskal-Wallis because of the normality change. But since the variance means so much more, you might want to go that way too. Remember, Kruskal-Wallis handles unequal variance too. So it's kind of a coin toss here. But if we do want to go the Kruskal-Wallis, there's a different way we need to do the post-hocs, and it's called the Dunn's test. And you can just do Dunn _ test for the tidy version, and then just do your P adjust version that you want to use. I use Bonferroni, and this is kind of our version of the Tukey or for the actual the Kruskal-Wallis non-parametric. And we have all the different combinations for response, and we see that there's 3 highly significant ones there that we see there too. So that's worked out too. So that gives you your other way around working on that stuff. I just want to show you one more thing, kind of a multiple testing corrections. It's a little bit confusing and a little bit more advanced. So if you remember last week we did our testing corrections, right? If you have more than 2 values, and let's say you're doing pairized t-tests, you need to correct for those values using methods like FDR, like Benjami-Hotspur, like Bonferroni, for example. And that is correct for multiple testing, right? And uncover problems with like maybe things mislabeled as false positive or whatever. And that was great when we looked at a bunch of genes. And ANOVA kind of took care of that for us, right? But what if we have a bunch of ANOVAs? It's kind of a confusing thing you may not have thought of. So let's imagine a situation. I created a new gene expression data set. Let's imagine a situation where you have 100 different genes, and each of those genes is expressed differently across 4 cancer stages, right? So if you wanted to look at each gene and just know if it is expressed different, like I want to know if these genes are expressed differently across those stages. So I kind of need to go for each gene, right? I'm like, gene 1, are you significant across these 4 cancer stages? And I can do an ANOVA there, and I can be like, yeah, there's a significance there. And I can do gene 2, I can do the same thing, right? Well, if I do that 100 times, that's going to destroy, that's like doing a bunch of t-tests, right? I'm creating a multiple testing problem, even though it's multiple ANOVAs rather than multiple t-tests. So what I want to do is correct for the ANOVA, right? So let's get our ANOVA p-values for each gene, right? So we do our ANOVA, for each gene here. I use the ANOVA.test, but then we also need to apply a corrections measures to those p-values. We have several different ones here. We use the to give you some different answers there, and then we just kind of evaluated the performance to see how well those did, summed it up here, and what we're seeing here is when we did this ANOVA, corrected for this ANOVA, the uncorrected version had 6 more positives. Now we baked in the data, if you look into the code, that we knew there was 10 positives. We knew that was true, right? Well, we found that the uncorrected version found 6 false positives. So there was an issue with that, right? And the FDR wasn't quite as good, right? Because of that. But when we made our corrections, all 4 of the extra methods were able to find those values and make them the true positives and give us great F1 and FDR scores. So just kind of another way of looking at it where don't get confused by trying to correct for different ANOVA, right? And if we want to kind of just plot those here and this volcano plot, I just kind of made GM points with a couple of horizontal lines. And if you look below the red, that's the Bonferroni significance. So we just kind of plotted right here our values by F statistic and log. We see all of these are looking good, and these didn't quite make it, right? So there's just a few genes that aren't showing such a high value because they are not the real values, right? So we caught all the real ones up here. These are the false ones. Okay, and here just kind of a distribution of our p-values, of our null p-values versus our real ones. And you can see our real p-values are really coming here and distributing, really low like we would expect them to do here, right? So that looks good. We feel good about that. It gives us another opportunity to look at things from a different direction, right? Now we're just going to run through a few practice exercises to get some reps here. So the first one, we're going to use some unconventional data, and we're going to try to decide whether Welch's test or the Kruskal-Wallis, work better for this data. So what I'm basically going to do is use my dose response data we used earlier, and I'll group by dose. So for each dose, we see differences in response here, cell death response, and let's look at the normality of this. So we group by dose, do the Shapiro, all normal, feel good about that. And then we do our Levine test, and we get equal variances no. So now we got a problem. It's parametric, but the equal variance is no. So kind of want to say Welch test there, right? But equal variance is so important. Well, maybe it throws the whole thing off, especially if there's outliers. Maybe that's something that Kruskal-Wallis, might want to look at. So let's kind of visualize the data real quick and just kind of look at the different dosages. This is a nice little Bach plot, filled by dose, a little jitter on there, and we're seeing the cell deaths getting higher as the doses are going up. So we kind of probably expect a good ANOVA overall, but we're not sure between them, right? So let's do both tests, just see what we get here. So for the ANOVA, we'll use ANOVA Welch test for our Welch on equal variance, right? Remember that could also be done with a one-way dot test with var.equal equals false. And let's go ahead and look at that result here. We have a low p-value, so it is significance. So we feel good about that. And we do our eta squared for our effect, which is 0.98. That's looking pretty good. But now let's try our non-parametric version, okay? The Kruskal.test, same input. I'm going to use the Kruskal underscore test here just to tidy it up. And once again, it has a pretty high F statistic and it has a very low p-value. And let's use the Kruskal underscore F size to get the actual effect size. Once again, a pretty high effect size, pretty much the same. ANOVA a little bit higher. So let's do our post hoc test on the Welch. We want to remember use the Games HAL test, and we see that everything is significant. Every single combination is significant. So just showing that every single dose is different there, or showing differences. And if we do, so every combination is significant, which seems a little bit odd. And then let's do our Kruskal-Wallis, right? We do the done test for that, right? Corrected by von Ferroni. This time they're not all significant, which seems to me a better answer. So if they're really far away, they are, but some of the ones aren't showing significance. So we have to look more into it, but it's possible that is a more robust result. And if we just compare the results, we're basically just show that they're both significant, and we're just seeing a little bit of a tighter level for significance with the Kruskal-Wallis. So I think you could go either way. ANOVA probably makes more sense, but based on the results, you could think about it of going either way. All right, so remember we did the two-way ANOVA. What about a three-way ANOVA? What if we want to look at three different things? I want to analyze the cell viability based on treatment and cancer type and p53 status. So if you're all these terms acting together, what is going on? Okay, let's do our AOV. We just do our times. Remember to get our interaction columns, get our little summary here, take a look at what we actually see from this. Let's see, what are we doing here? AOV, and we get our statistics, and we're seeing there's significance in treatment like we've seen before. We'd expect that. And we see significance with treatment interacting with cancer, which we've seen before. So that's not a really surprise. And we're seeing it in treatment with p53. So there's some interaction with that as well too. But interestingly, there's not a difference between interaction between all three of them. So weirdly, treatment has an effect, but cancer type and p53 status alone don't, like in a vacuum. But if you interact them with treatment, then they do have some effect. Cancer and p53 don't have an effect, and all three together don't have an effect. So that's kind of what you're looking at right there. And let's get our effect sizes. Just use the eta squared for all of them. And we're seeing the treatment has a very large, and the other ones, like, let's see, treatment is very large, and treatment cancer has medium, treatment p53 small. So that's kind of our range of effects of things that are actually happening. And we're going to make a little three-way interaction plot like we did above. We'll split these. That's our one-way, and then that's our two-way, just to kind of see what's going on. As you can see, as we go to each cancer type, we're not seeing much of a difference between them, but inside of each one, we are seeing a pretty strong effect there. All right, so let's do our final one. I kind of just threw this in there just for fun, to get you kind of thinking about creating custom functions for your work that just makes things so much similar going forward, even a year later when you pull up a ANOVA problem again, right? So I'm going to create a custom function for ANOVA with assumption checking. Now the caveat here is I'm going to have to assume normal and equal variance, because it would be a much more challenging problem to be like, well, if you're not normal, then choose this, blah, blah, blah. But you can work on that. You can do that and you can make a full function that has every possible scenario. This is going to be a scenario where we know normal and equal, or we can at least just run it and see if that works out, then it plots out right. So basically, I just have started our function will be called perform ANOVA analysis, and our input is our data, and our formula string are our treatment versus cancer type, whatever. So like that's our formula. So we put our formula in, when we put it in, it's going to be like our actual data, and then our formula here, p53 by stage. So It's basically taking that formula, it's doing an AOV on it and summarizing it, and then it's doing a Shapiro.test or underscore test using the tidy version here to get our normality. And then we are using our Levine test for our equal variance, and we're kind of just printing it all together with our effect size and a Tukey analysis as well too, and just kind of summarizing it all up for you. And you can see here, you can put the name, the formula, we have our assumption checks, we have our results, we have our effect size, we have our Tukey. So we have everything we need for a complete analysis here. And if you checked real quick and knew those were yes, then you could just run this function and it would give you everything you need. Feel free to steal that function and do some extra stuff with it, whatever you need, if it can help you out. And then how can we visualize this? Well, we have the model, the AOV 53 stage, right? Let's just make that model, get our Tukey stages, see, Turkey. And let's try to look at these and see what they would look like, right? Well, I just want to get my Tukeys first and basically kind of did like I did above and make that GM error bar plot here, right? So I'm just grabbing the Tukey values. I'm just doing my ANOVA, doing my Tukey, grabbing those Tukey values and remaking my plot showing the differences here. As you can see here, there's a couple stages that don't show significance. Let's see, stage 3 to 4, for example, not enough change. Stage 1 and 2, not enough change. But all the rest do show significant change. And then, then I'm just looking at the expression versus P53 to form this, this box plot here, which is really simple. GM call. Remember, you can do GM bar identity or GM call for your box plot, and that just kind of gives you a good visualization of everything that's going on there. All right, so that worked out great. Our summary of the week. We were able to go through a one-way ANOVA. We can actually compare means across more than 2 groups and just kind of see if there's a difference. And it maintains our error at 0.05, and then we can have a global interpretation to know if we need to go in further to look more deeply, to look at pairwise comparisons with our post-hoc tests, which include the Tukey, Dunnett for just control, or Bonferroni for conservative correction. It's the tightest correction. You could also use, this is more pairwise. You could use those for your post-hoc test. And remember, for your two-way ANOVA, you test 2 factors simultaneously, and you get the interaction as well too. And if you remember, if your correction methods, so if you're independent all the way, you can go ANOVA. You can go your Tukey methods that we've talked about. If you are unequal variant, then you can choose the Welch. You can use the game howl for your Tukey, for your post-hoc. If you have non-parametric, you use the Kruskal-Wallis, and then you use the done version for that for your post-hoc. And then for the effect size, you use the eta squared, omega squared for Welch and normal ANOVA, and you use the Kruskal effect size function for that too. That's kind of all your different ways you go, and then choose your multiple, testing values by how strict things need to be, whether you're going for exploratory analysis or you want very tight last answers there. Here's kind of a summary of all of that. Next week we'll be covering one of my favorite things to do, survival analysis, where we'll understand time to data, tell how populations have different levels of survival, and they look at Cox proportional hazards, which are just kind of advanced survival models where you're looking more in depth and what's going on between different factors within those models. I also made an additional assignment for you guys. It's a little bit complicated, but it's something you guys couldn't tackle. It's using very similar data that we're using here, and it's just building upon that to do a little bit more advanced things that maybe we didn't have time for here. So we're doing a multi-drug comparison for the first one. We just need to do ANOVA, make some publication-ready box plots. For 2, we're looking at the factorial design to do 2-way ANOVA. And we're doing a non-parametric analysis for our question number 3. And lastly, we'll be doing a multi-testing simulation to look at the correction for different values and large high-throughput gene analysis. And for additional resources, you can look at how to use ANOVA and R, look at the e-means package, look at the multiple comparisons guide, look through the R for statistics. There's plenty of different resources out there to look at how to do this, but I think I gave you a pretty good pretty good way of looking through it here today. So this concludes our third week of the R statistics workshop, covering ANOVA, multiple comparisons, and our post hoc analysis. To build upon our t-test from last week, I look forward to our survival analysis for next week. Please check out the additional assignment and additional resources for more practice using R statistics. And thank you guys for being here, and I hope you guys learned something.